Hey guys, today is actually Thursday the 26th, and I'm getting a jump on this next lesson, module number 13. Y'all know we've only got this module and one more module left, and we're done with chemistry. We stopped right after, look at that, we stopped right after module 14, so I'm really excited that we're kind of wrapping up chemistry. And so here we are in my kitchen. Welcome to the second edition of Quarantine Chemistry. So I'm going to start us in prayer and then we'll get going, okay? Dear Heavenly Father, thank you again for the media that we can come together and do chemistry this way. When we can't be together in a classroom, that we can still get the things done that we need to get done. Lord, I pray that you be with each student and give them the ability to sit through an hour or so of watching a boring old video of an old lady trying to teach them chemistry, especially on days when it's so pretty outside. Lord, thank you for this beautiful day. Lord, I pray that you will continue to bless those families that are suffering and let them see who you are, Lord. Show yourself, reveal yourself to them as Jehovah Rapha, the God who sees and heals. Lord, I pray that you be with all these children and keep us healthy, put a hedge of protection around our families. All these things in Jesus' name. Amen. Okay, I'm going to shut my door over here so we will quit hearing so much noise. Okay, I'm actually expecting to hear my husband here in a few minutes come tell me he's hungry, so I'm really hoping that that doesn't happen while we're right here, because then we're going to have some action in the kitchen, and hopefully we can get this finished first. Okay, turn to page 448. We're going to start talking about thermodynamics. We're going to go from page 448 today to page 465. Okay. There's a lot of really cool information here. You're going to have to read a lot of it to try to catch on to it, and we're going to go over the math. We're going to focus on some math, but we're also going to do some reading, okay? Things that you learned last week kind of carry over into this week as far as endothermic and exothermic types of reactions, and that's what we're going to be looking at today. So I'm going to start reading. Y'all stick with me. Page 448. In Module 10, we learned about endothermic and ectothermic processes. When solutions dissolve exothermically, they release energy, causing the solution to heat up. When they dissolve endothermically, they absorb the energy from their surroundings, causing the solution to cool down. When a solute dissolves in a solvent, no chemical change is occurring. We'll examine exothermic and endothermic chemical reactions. We're not talking about the physical reactions, we're talking about the chemical reactions. Almost all chemical changes either release or absorb energy. Now, we're going to talk about a big section called enthalpy right here. And you're going to see this means enthalpy. And we're going to talk about that a little bit more in just a minute too. So, bottom of page 448, chemical reactions can be exothermic or endothermic, like we talked about just a second ago. If a reaction is exothermic, energy is released in the process. The energy as a product of a chemical reaction. So when we're talking about an exothermic reaction and we're talking about it being released, we're talking about the product. So that's going to be in a chemical reaction. This is the product. Oh, you can't really see that, can you? Let me adjust some of the windows in the back. But what we're talking about, this is the product, this is the reactants. So as we're talking about endothermic and exothermic reactions, we're going to talk about how the exothermic release energy, and they're going to be on the product side. Let me close a window back behind me here. Did that help? Yeah, that helped a little bit. Okay, if not, I'll just close another one. We've got 3 big windows back behind me, or in front of me. So now, if a chemical reaction is endothermic, it's just the opposite. The energy is on the reactant side. So the energy is going to be over here in an endothermic reaction. Over here, it's going to be an exothermic reaction. If a chemical reaction is endothermic, we can think of energy as a reactant in the chemical equation because heat is required to make the reaction go. Okay. Now, energy cannot be created or destroyed. Remember that from last time. Nevertheless, we will think of energy in chemical reactions in the following way. I have highlighted this little blue section here. It's important for you to know. When a reaction is exothermic, energy will be thought of in the product. If a reaction is endothermic, energy will be considered a reactant. So, just a convenient way of thinking. Energy, we learned that there's 2 kinds of energy, potential and kinetic. Potential energy is stored, and kinetic energy has motion. It's the part that moves. Let's see, blah, 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 blah. Sometimes I skip through here, and I kind of figure it out on my own. Potential energy is energy stored, so when a reaction occurs, it changes to kinetic energy. But again, it's not created or destroyed. It just changes. A chemical reaction is exothermic. Potential energy that is stored in the reactants is converted to the kinetic energy. In a chemical reaction that's endothermic, the kinetic energy in its surroundings is absorbed and converted into potential energy for the product. It's converted. It doesn't say that it's changed. It doesn't say that it's created, rather. It's saying that it changes. That's a big difference. Look at the bottom of page 449. If we react hydrochloric acid, which you should recognize as an acid, it's hydrochloric acid, with NaOH, that's sodium hydroxide. OH tells you OH is a base. Remember, OH is the base. Oh, it's a base. Remember that one? Okay, the following chemical reaction occurs. HCl plus NaOH equals H2O NaCl. Now remember how we made our little formula? How we figured out what was going to be on the product side. We predicted our product. How we brought these down. And when you bring the 2 outside together, that's 2 H's and an O, we know that's going to be H2O. And then we've got sodium, which is an Na plus 1, chlorine, which is Cl minus 1. Positives come before the negatives, so it's going to be NaCl plus H2O. Remember when we did that? Yeah, we still got a glare. Let me close some of the windows. I'm just pulling the curtains too. That didn't even help too much, did it? We'll come up with some better solutions. Yeah, that's better. Okay, so put on some artificial lights. All right. So this is an example of the reaction that we have down here on the bottom of page 449. If you were to perform this reaction, the reaction vessel gets really hot. Why? What kind of reaction gets really hot when you touch it? Is it endothermic or exothermic? It's exothermic. Exothermic puts heat out, okay? Energy is released. And the reaction gets hot, it's exothermic. So look at how we would write that. I guess I better put that back up. HCl, where'd it go? Plus NaOH produces NaCl plus H2O. And since we know it heats up, it says that it's an exothermic reaction. In the experiment that they did, they found out that the vessel got hot, so we know it's exothermic. So we're going to put here plus energy. That's released energy. So in the same way, continue through the page, you're going to see that there's another reaction. And this reaction tells us that the vessel gets cold. If the vessel gets cold, then the energy is added to the product side, to the reactant side, because it's endothermic. Endothermic is on the reactant side. So, every substance in nature contains potential energy. Every substance in nature contains potential energy. Remember, this countertop has got energy in it. Even though we can't see it and we can't feel it, it's still moving. 1 minute. Please quit coming in and out of that door. Thank you, sir. This is what happens when you shoot video at home in the middle of the day. I sent my kids outside to play, and they are opening and closing that basement door. It's making our security system open and close. Going to drive me crazy. And they know they're not supposed to do that too, but they know I'm doing this, so they're seeing what they can get away with. Getting ready to go get me a belt. Whoop me some babies. I'm hot. Okay, believe me. Okay, let's see here. Now, every substance in nature contains the potential energy. They did it again. The energy stored in a substance is called enthalpy. The energy stored in a substance is called enthalpy. Now, chemists use H to symbolize enthalpy. Chemists use H to symbolize enthalpy. In a chemical reaction, substances are both consumed and produced. We know that. As a result, enthalpy changes in a chemical reaction. When this happens, energy is either released or absorbed. We either come up with an endothermic reaction or an exothermic reaction. Now, don't know why they chose H, because that's kind of confusing, isn't it? But the symbol for enthalpy is delta H. Delta, does anybody remember what delta means? Delta means change. So, change in enthalpy, that is what you're reading. Delta H is change in enthalpy. But it's really just still called enthalpy. I know. The energy change that accompanies a chemical reaction. That's what enthalpy is. It is a chemical, the energy change that comes with a chemical reaction to either exothermic or endothermic. Enthalpy, delta H, they both show as delta H, even though it just means enthalpy, okay, because it is the change. So, bottom of the page, 450. Remember, enthalpy represents the energy change associated with that chemical reaction, and as a result, you'll have an energy unit attached to it. Remember from the last module that the two major units are joules and calories. These units are related to each other as follows. Remember from last time, 1 calorie equals 4.184 joules. So, since most chemical reactions involve quite a bit of energy, the units that you'll probably see in enthalpy are called kilojoules. So you're going to see that's written as kilojoules. That's what we're going to be using a lot of. Now, page 451, first full paragraph. Let's read that together, please. Kilojoule and kilocalories are not the only units that you'll see attached to enthalpy. As you might expect, the energy released or absorbed by a chemical reaction depends on the amount of the reactants that are consumed. I feel some stoichiometry coming. That energy released or absorbed by a chemical reaction depends on the amount of the reactants that's consumed. After all, if you were to burn 1 kilogram of wood, we would produce more heat if we were to burn if we burn 1 kilogram of wood, we'll produce more heat than if we burn 1 gram of wood. As a result, the value of enthalpy depends on the amount of reactants undergoing the chemical change. To account for this, chemicals sometimes use enthalpy as a reaction of a mole-to-mole basis. Stoichiometry. You'll sometimes see enthalpy as units of kilojoules per mole or kilocalories per mole. These units indicate that the energy change represented by enthalpy occurs when 1 mole of reactant gets consumed in the reaction. Therefore, if enthalpy of 50 kilojoules simply means that after 1 mole of reactant undergoes the chemical change, there is a chemical change of 50 kilojoules per that mole. Now, again, look at the blue in the page. Enthalpy is positive for endothermic and it's negative for exothermic. That is something you're going to need to remember. Star it, write it down, put it in your notes. You're going to have to remember that. I'll even write it up here. Endo is going to have a positive reaction. Exo is going to have a negative reaction. Okay? The enthalpy of these different types will be a positive or negative. Okay. Now, it says here in my note that this is the same concept as 12.3. Like what we did the last time. You remember how we did the Q's and sometimes it's positive and sometimes it's negative? It's the exact same process here. It's the same thing, except we're talking about enthalpy. Okay, so it is a little different in the units that we're talking about. If we're told that a reaction has enthalpy of negative 123 kilojoules per mole, we know that the reaction is exothermic. Negative exo. We're going to know that just by that number. Then, on the other hand, if it's 56 kilojoules per mole, we're going to know that it's endothermic because it's a positive number. Let's look at example 13.1. I'm going to flip over. I've already done the work, so we'll flip it over here and see if I can find it. Okay, got it right here. Okay, the first thing that we're going to do, I'm going to leave this right here, okay? I'm going to work on this side of the board. When CH4 undergoes complete combustion, that's going to tell you what kind of reaction it is, and you're going to have to remember how to write out that kind of reaction. Remember that in a complete combustion reaction, your answer is always going to have CO2 and H2O in it. Your product is always going to have CO2 and H2O. So whatever you have, you're going to have to, in the reactant side, it's always going to react with oxygen, and your product is going to be CO2 and H2O. So, it undergoes complete combustion. The change in enthalpy of the reaction is negative 803.1 kilojoules. Write a balanced chemical equation representing this process. Include energy in your equation. So all we have to do is know how to write a complete combustive reaction. So let's start with our given. Let me see if you can see that well. Let's stick with our dark colors. My given is CH4 complete combustion. We'll do that in a second. But my enthalpy, my delta H is negative 803.1. I need to find the balanced equation. I need to write my balanced equation. Make sure I don't drop my board. We know how that works out, don't we? Representing this process and label where the energy is. Okay, so my plan is to balance. I've got CH4? Yeah. CH4 in a complete combustion plus O2 produces CO2 and H2O. Now, I got to balance this out. I could go through my little lines, and that's what you're going to have to do, but I'm not going to do it on this board because this board is limited. So, I'm going to write in red, right up above it, what I found. It's going to take 2 oxygens. I can't see that too well. It's going to take 2 oxygens, and it's going to take 2 waters. Okay? So, here I have my balanced equation. Now, I have to add in that enthalpy. And by looking at it, is it endothermic or exothermic? It has a negative mark here. That means it's exothermic. That means it's going to go on the product side. So on this product side, I'm going to write plus 803.1. Now, the negative just shows me that energy was released. I'm still going to put a plus sign over here because it's energy that's released. The negative tells me what the enthalpy is, the change. But this is still going to be a plus 803.1. Okay? You can see that worked out on page 452. Now, we're going to do one on your own together. Let's do on your own 13.1. The formation of ammonium nitrate has a, let's see. Let's not do A. Let's do 13.1b because it's a little different, okay? And that's what we want to look at is the difference. So, the decomposition of manganese 4 oxide, which has an enthalpy of 519.7. So, I know I have, let me find it. There it is. My given is that I'm doing a decomp of manganese oxide. Okay? And then I need my, also given is my enthalpy of 519.7, yeah, kilojoules, okay? What I'm going to find is the energy. I'm going to figure out where to put that energy. What kind of reaction is it? How do I know what kind of reaction it is? Well, so I'm going to find the, first I'm going to balance it, and then I'm going to find the energy. What am I doing? Okay, my plan is I'm going to balance it first. So I'm going to do MnO2. It says that this was a decomposition. That means I got to break that down. So it's going to be Mn plus O2. Now, this is balanced, okay? But I have to figure out where that energy goes. 519.7, is it positive or negative? Well, there's no negative sign in front of it, so it has to be positive. That makes it an endothermic reaction. The endothermic reaction takes place on the reactant side. So the endothermic reaction will be MnO2 plus 519.7 kilojoules produces Mn plus O2. Okay? And that's it. That's all you have to do for this specific problem. It's only wanting you to find where the energy is found. Is it found in the product or the reactant? Okay. I'm going to take a quick pause.